Okay, so here's where we were last time. We were talking about this example here, and specifically this is an example of how to use Stokes' curl theorem. Remember Stokes' curl theorem? We walked through the reasoning, sort of the rationale, motivation, you might call it, for this last time. And the idea is that circulation is an accumulating quantity over surfaces. So the total circulation is a surface integral of what you might call circulation density. We'll come back to that in a few minutes. But picking up with our example, we'd already kind of talked through that this curve over which we've been asked to compute a circulation is a boundary. Specifically, it's a boundary of this surface S here. So if we've been asked to compute a circulation over a boundary, that's what makes this applicable, or makes Stokes' theorem applicable. After all, here it is. Stokes' theorem is about circulations over boundaries. And now that we've established that it's a boundary, we can rewrite it as a flux. And I think this is about where we ended last time. So Stokes' theorem kicks in right here. Okay, let me pause real quick. Is everybody on board so far? This all looks familiar. Okay, good. Okay, so let's talk about orientation a little bit. This is a little bit of an annoying issue, but we always do have to think through orientation. I'll remind you, it is one of the significant ideas of the course relevant to solutions. Points come from, demonstration of reasoning on the relevant points to a problem, right? So orientations do tend to matter quite significantly. On a 20-point question, orientation could be 4 points, sometimes 5 if there's not that much else going on in the question. It depends. But in this case, the orientation on our new surface here is downward. Now, why downward? It's downward because the curve that that we were given initially, the curve whose boundary, the curve that is the boundary of our new surface, was oriented that way. And if you think about, thumb, finger, swirl, side swipe, the usual rule, if we had oriented our new surface up, you look at the fingers of my right hand here and see which way they want to point, and that would make the swirls go the wrong way. But if I orient my thumb downward, again, right hand, look at the fingers, see how that makes a swirl. Let's go the correct way. So, the orientation of the surface has to be downward, and this is something that you just have to kind of trial and error in some sense. Good news, there's only 2 options to try, right? So, try one. If it works, super. If not, the answer is going to have to be the other one. Go ahead and establish, anyway, right? But it's not like you're going to be trying and failing over and over again. Okay, so all of this said, here's our curl, our normal vector. We just agreed was there. The curl of the vector field is something that you can explicitly compute. That's just some partial derivatives. Make sure to know the formula, but altogether it's just some partial derivatives, and it ends up being 0, 0, 2. The normal vector, of course, as we just agreed, is 0, 0, -1. And the integral turns into a really easy integral, 2 times the area, and so boom, answer. How we doing? Everybody's happy? All right. Okay, so real quick, let me remind you, we had this eyebrow-raising moment last time that I made reference to this thing here, circulation per unit area. Came up with the term circulation density, which I like very much. And then I asserted without computation that if you crank this out, compute what it ends up being, it's this formula right here. And the eyebrow-raising part is that this seems to depend somewhat on the surface. We would have kind of expected that it would only depend on the vector field. After all, look at the formula in the divergence theorem. Flux density. There's no tangent vectors or normal vectors or anything. It only depends on the vector field. Look at Green's operator. Only depends on the vector field. So how come this doesn't depend only on the vector field? How come the surface kicks in? So what I want to point out is, eyebrow raising though that is, it is not our first time to see that. When we talked about the fundamental theorem of line integrals, one version of which is this, right? You can see density here, change density, as I like to call it, is partly dependent on the curve. There's that tangent vector. Tangent to the curve. So the orientation contributes to the density in this old example as well. So this is not really unfamiliar territory. Now, the point of view that I took on this at the time, and I think this is a good point of view, I find this very satisfying. Keep in mind, I thought even then that these two things should be kind of paired together. Both of the tangent vector and the little ds scalar are telling you about a little piece of curve, after all. So I like to incorporate them together as what I call the dx vector. Right? And with that in mind, now let's think about not how do I relate quantity to size, but how do I relate quantity to what you might call oriented size. Now, that's a weird way to think about this, but keep in mind that this is also not our first time to find weirdly constructive ways to think about certain things. I think this is another one. The dx vector is telling you about the orientation of the curve, and it is telling you, by virtue of its magnitude, about the size of a little piece of curve that we're interested in. So this has an orientation and a size. Calling it oriented size, I think, really makes a lot of sense. Right? So with that in mind, I proposed that maybe we should call this thing an oriented density, because instead of relating quantity to size, this is relating quantity to oriented size. So the term oriented density, I think, is plausible. I feel like this is reasonably plausible. So oriented density, and don't forget our quantity in question is change, and thus the term oriented change density. All right, now there's a lot to digest there. Give yourself enough time. Re-listen to the recordings if that might help to digest kind of the point of view here. Let me point out another thing about oriented change density. You can look at what's inside of it. Right? You can make sense out of the two different sort of geometric aspects of this gradient vector. All vectors have two geometric features, a magnitude and a direction. Keep in mind, the magnitude tells you how steep is the mountain. Right? It tells you how fast is the function changing. Now, asterisk, how fast the function is actually changing depends on which direction you're going. If you're hiking on a mountain, if you're walking on a sideways on the side of a mountain, you're not getting a lot of change of altitude. Fair, right? So when I say the magnitude tells you how much the function's changing, it's telling you how steep the mountain is in the uphill direction, of course. Right? So the u vector is telling you the other aspect of that. It's telling you, yeah, sure, the magnitude is how much of the quantity in question are we talking about, and this says in what direction is that happening. Right? U is saying uphill. That's U for uphill, perhaps, or maybe it's U for unit vector. Take your pick. But U is telling us which direction is uphill. Magnitude of the gradient is telling us how steep is it in that direction. All right. Now, what I'm going to do is I'm going to take this sort of the pattern of analysis that I've done for the fundamental theorem of line integrals there. I'm going to do the same thing now for Stokes' theorem. Here's the first version of Stokes' theorem that we wrote down. Right? And again, kind of weird that our notion of circulation density, so the relation between quantity and size being area, ds here, has this normal vector in it. And again, that's weird. And why is there a normal vector? Well, think of it this way, these things really ought to be grouped together anyway. Right? After all, both of these are telling me about a little piece of surface. ds is telling me the size of whatever little piece of surface I'm looking at, and the in vector is telling me about the orientation. How is that piece of area sitting in space by what little unit vector is it perpendicular to? So both of these little pieces of information are telling me about the same little piece of size, and thus I like to group these together as the ds vector. Totally analogous to up here, I like to group these together as the dx vector. So, okay, fine. Now let's reconsider circulation, thought of as this. Reconsider, how should I interpret this thing? Well, this now is the thing that you multiply, okay, dot product, fair, but that you multiply in a sense by oriented size. Just like dx is oriented size, likewise ds is oriented size. It's telling you about both the size and the orientation. So oriented size, and as such, curl, I propose, should be thought of as an oriented density. And what kind of oriented density? Well, we're talking about circulation after all, and so therefore oriented circulation density. And that's a lot of words and a lot of syllables, and it's kind of intimidating and scary sounding, I freely admit. But notice the pattern, though. Every aspect of this little calculation that we're doing here is completely analogous to a corresponding idea up here that we talked about in context of, gradients and the fundamental thermal line integrals, uphill and stuff like that. Okay. All right. So likewise, I can look at this vector, I can look at this curl vector, and it too has sort of two features, right? Any vector has a magnitude and it has a direction. The magnitude is telling you what I'm going to loosely call the sort of the overall circulation density. In other words, altogether, to what extent is the fluid, to what extent is there a rotational aspect to this fluid? That's what the magnitude of the curl vector tells you. But it doesn't tell you in what way that is realized. In the same way that the magnitude of the gradient tells you how steep the mountain is, it doesn't tell you what direction that uphill is. Right? So that's the job of the u vector here. This is telling you what is the direction in which that rotation is actually realized. Is it rotating around, an axis like that? Or is it rotating around an axis like this? Or perhaps is it rotating around an axis like that? That axis is identified by the unit vector and the direction of the curl. Okay, all right, let me draw a picture of this. Here we go. Here's our curl vector, our oriented circulation density, right? And that's telling us, again, two things. It's telling us, by way of its magnitude, it's telling us how turbulent of a tornado is this. Is this a lot of circulation of fluid? Right? Is this a category 5 kind of a tornado? Or if there's a shorter magnitude, then maybe there's just not as much rotation of fluid. Right? And by the direction that it's pointing, it tells us what this axis is that the rotation is around. Okay, how are we doing? Is everybody with me? Buy it? Okay. So now this business here is just kind of this is for intuitive satisfaction purposes. What I've got on the screen here doesn't prove anything. I just want you to have some reasonable sense of plausibility that you would should expect the normal vector to make a difference when you're talking about little pieces of circulation. And in particular, supposing that we're looking at a piece of surface here. This is my little piece of surface, and I want to know how much boundary circulation is realized on that little piece of surface. So in the top picture here, this is sort of two scenarios. Let me separate them like so. In the top scenario, notice that the fluid is rotating around kind of along the same direction that the boundary that the circulation is measured on is actually going around. And keep in mind, circulation is a line integral. Line integrals are measuring the extent to which the fluid is flowing along that curve. So to what extent here is the fluid flowing along the curve? To what extent is the rotation of the fluid creating actual circulation on this boundary? Well, quite a bit. It's flowing like directly around that boundary. So we would expect here that the circulation should be large. And now let's think about what are the vectors doing. Well, the curl is like that. The normal vector is like that. And this dot product, curl dot in, also large. Right? The fact that the fluid rotation and the boundary rotation are in the same plane, or in parallel planes, is geometrically simultaneous with the fact that their perpendicular vectors are parallel. Yes?
So when you say circulation and free rotation, they're the same thing.
Well, I mean, the terminologies do get used a little. I'm trying to avoid crossing my terminologies, but when I'm talking about how the fluid is moving, I'm trying to make a point of saying the word rotation, right? Because technically in this class we've defined circulation as an integral along a boundary curve, or along a closed curve. So I should say the rotation of the fluid and the way the boundary curve is oriented, those combined is what creates circulation.
So can we say the sum of the micro rotation?
I hesitate on that because we haven't really defined. I mean, when I say rotation, I'm just trying to describe that generically speaking, that if the fluid's kind of doing this, right? So I'm in some sense going to some trouble not to define that because I don't want to get too into the weeds. But circulation is a line integral. Circulation is literally the line integral of of a vector field along a boundary curve. Is that satisfying? Okay, cool. Okay, so what you see here is that when the fluid is along the boundary, then the curl is along the normal vector. And by contrast now, let's consider another scenario. Here's a perfectly plausible scenario that our same fluid, but now look, we have a different little piece of surface here. And let's talk about the way this boundary is going. Here, the fluid is rotating this way, but the boundary is rotating kind of that way, and I don't have the eye-hand coordination to do these at the same time, but the fluid is going like that, the boundary is going like this, and they're just in different planes. There is basically no sense in which this rotation of fluid is realizing in a line integral along this boundary curve. They're just in different directions. And tracking with that perfectly is the fact that the curl of the vector field and the normal vector for the surface are also pointing in different directions. So when there is circulation, when the rotation is along the boundary, normal dot gradient detects that. And when there really isn't, normal dot curl detects that as well. Right? When this dot product is large, the circulation is large. When the dot product is negligible, the circulation is negligible. That kind of makes sense, right? At least it's sort of consistent with these examples. So my goal here, again, is not to prove anything. My goal here is to make it seem kind of reasonably plausible that the formula for for circulation density should have this normal vector in it. That's plausible. Okay. All right. Moving along. Okay, so a couple of physical examples. This first one we've already talked about. We've already talked about two-dimensional fluids, and the idea is if I like to think of water, for example. Right, here's a fluid flowing along, sort of imagine this being the surface of a river, and the water is flowing faster, farther away from the bank of the river, and slower near the end, near the edge. Well, what does the floating leaf do? It does exactly what the water tells it to do. If you know the water's velocity, then you know the leaf's velocity. They're the same. But now let's talk about rotation. To what extent is the leaf kind of turning as it goes? Well, look, it's being pushed harder on that side. It's being pushed quite a bit less hard on that side. And so you would expect that it would kind of have a rotational aspect as it floats downstream, right? And the thing that measures that is Green's operator. That's an easy sort of physical interpretation of Green's operator. Okay, along those same lines, curl does a very analogous thing. Now, we're in 3 dimensions to talk about curl. I have to have a completely different metaphor here because I don't want to imagine myself submerged underwater. I find it uncomfortable. Right? So I'm going to imagine the fluid being air, and so this represents the velocity of air, let's say in this room, a certain amount of airflow. I think I hear an air conditioner on here. Yeah. So there is an airflow in here, at least a little bit. I wish there were more. And now imagine that there's little floating balloons, right? Because I need them to be 3-dimensional. I need them to be able to move 3-dimensionally. I need them to be able to rotate kind of in any direction. So I'm imagining these perfectly balanced balloons that just follow along with the air as the air tells it to. So with that in mind, the air's velocity gives you the balloon's velocity. Of course, balloon does exactly what the air tells it to do. And then likewise, whatever rotational aspect there is to the air movement, that's measured by curl. Remember, curl tells you how much and in what direction do we have that rotation of the air. Well, the balloon's going to do what it's told in that sense as well. Whatever axis the air is rotating around, that's the axis that the balloon will be rotating around as well. Everybody all right? Makes sense? And if you want to know how much the balloon is rotating, well, how much is just a scalar quantity, just a matter of magnitude, and then you just look at the magnitude of the curl vector itself. So longer curl vector, greater magnitude of curl vector, more rotation. If the curl vector is twice as long, there's twice as much rotation. Like that. Okay. Is everybody happy with that? And furthermore, does everybody see how curl is playing an analogous role to Green's operator, just in a 3-dimensional context instead of a 2-dimensional context? Okay. All right. Okay. All right. Different physics application. I'm going to try to keep this short. This does get more physicsy and in a way that is less familiar, and in a way where there's less convenient intuition. I am a really big fan of the idea that I've talked through with y'all last time about how you can think of gravity as communicated by the matter emanating little particles called gravitons. Gravity is basically like light in that it's made up of little particles that flow that are emanated by things that emanate them, right? LEDs create the flow of photons. Matter creates the flow of gravitons. Same thing. Same metaphor, different details. Okay, I don't have any analogous point of view on magnetic fields. So I'm going to just say what has to get said here, and then we're going to kind of just move on from that. We start off with a flow of charged particles. So that's the premise of the circumstance that we need to describe here, is that we have charged particles that are moving as a fluid. And keep in mind, if you want to represent the flow of a fluid, we do that with a vector field. You do need a scalar factor indicating the density of the whatever the fluid is, in this case charged particles, so we call that charge density. Just for convenience of terminology, this is called the current field. Okay. When you have a current field, when you have a flow of charged particles, empirically, we notice that creates something called a magnetic field. It just does. This is just empirical. I'm not aware of anyone having anything that could be reasonably called an explanation for why this is. It just is. So, weirdly, when you have a flow like that, the magnetic field has a tendency to go sort of, you might even say, tendency to rotate around the current. Again, empirical. I have no idea why whoever built this world built it this way, but this seems to be the way this world was built. So, so here is the one way to say this, and that is that there is a proportionality between current, namely the total flow of your fluid through a given surface. If you just literally count particles per unit time passing through a given surface, that's called current. So there's a relationship between current and what we call magnetic circulation. So keep in mind, lowercase sigma is how we represent circulation. B is our notation for our magnetic field. So this is magnetic circulation, they call it. So said differently, the more of a flow of charged particles there is, the more of a circulation of magnetic field there is going sort of around it. That just is what it is. Okay. So, that said, with this empirically noted, let me point out what current is. Current is quantity of fluid per unit time. That's literally flux of the flow field. That's kind of the definition of flux. Right? If you have a vector field representing the flow of a fluid, flux tells you quantity per unit time of fluid passing through your surface. Okay. And then this, of course, is just Stokes' theorem for the magnetic circulation that we have. So altogether, this observation here that we call Maxwell's fourth equation, notice that I can line that up with this equation right here, these integrands needing to be equal, which we also call Maxwell's fourth equation. These are just two different versions of the same equation. In the same way that, going back several pages, let's see here. Here we go. In the same way that these two equations are morally the same equation, these two equations were related by the divergence theorem. Likewise, here we go. Likewise, these two equations are related by way of Stokes' theorem. Okay. So yeah, these are Maxwell's fourth equations. So by the way, there's also a Maxwell's second equations and Maxwell's third equations, and they too can be related to the divergence theorem and the curl theorem. It's just that they're even more physicsy. And it's not that we couldn't do them, it's that we don't need to and don't have time, and this is not a physics class. But anyway, when you do take a physics E&M course, or maybe an engineering E&M course, what have you, be on the lookout for how Stokes' theorem and the divergence theorem can give you powerful connections between the various different facts that you can say about electric and magnetic fields. All right. Everybody all right? Questions? Okay. Here's some more old news. This is literally a copy-paste from Chapter 6. We talked about how gradients are path-independent. We talked about how every path-independent vector field has this feature that all closed line integrals are zero. In fact, that's just an alternative phrasing of path independence. So we know that the three equations that I have there in green are all equivalent. Regularity assumptions, assumed. And then I also made this observation that if you look at these two statements are actually pretty much the same statement. I mean, if you have a double integral of an integrand, and this double integral is not only equal to zero, but for every domain, you'll always get zero. The only way that's possible is if your integrand is itself zero. So we talked about that back in Chapter 6 as well. So we have 3 green statements that we see to be equivalent. We have 2 blue statements that we see to be equivalent. What connects them is Green's theorem that says closed line integrals can be computed as double integrals of Green's operator. Right? So it's because of Green's theorem that we can make this connection, establish that all 5 of these conditions are equivalent, and therefore declare that we have a local test for something being a gradient. If I want to know if something's a gradient, right, is a vector field that I'm given a gradient? Oh, well, compute Green's operator and just see if you get 0. If you get 0, yes, it's a gradient. If you get something that's not 0, then definitely not a gradient. Okay, that was all previously covered. Why am I showing it to you again? It's because now we have the necessary tool to make the 3-dimensional version of this argument. So you may recall I kind of wrote at least this part down in Chapter 6, and I just kind of asserted that the curl plays the analogous role. I never explained why. I couldn't explain why. I gave you my excuse. This would require the use of a 3-dimensional theorem we don't have yet. Y'all may recall me lamenting. So, here's the argument. Again, we know these 3 statements are equivalent. Now let me point out these 2 statements, seemingly unrelated, but these 2 statements in blue. If I have a vector field called curl F, whatever, but if I have a vector field, and for every surface, the flux is 0. Every surface. Really? Every surface. The flux is always 0. There's only one way, and that is if that vector field is itself 0. Okay, so totally analogous. And how, again, do we connect these statements? Well, I need a theorem that relates closed line integrals to fluxes of the curl vector. And as of Chapter 6, we had no such theorem, but as of now, we do. Stokes' curl theorem is exactly that. It says that every closed line integral can be computed as a, again, assuming regularity. We have to assume regularity of everything in sight, no singularities, no discontinuities, nothing bad, right? But all regularity assumed, closed line integrals are fluxes of the curl through the interior surface. So with Stokes' curl theorem established, then that connects all the dots. That means we have a local test for whether something is a gradient. If you have a vector field, you want to know it's a gradient, compute curl. Curl's the thing. See if you get 0. If you get 0, yes, you're looking at a gradient. If you get not 0, then no, you're not looking at a gradient of anything. Okay. All right. So the purpose of this page is just to close that previous conversation. Previously this kind of This bit here was kind of dangling, unestablished, but now that we've got that filled in, we're done talking about the local tests for gradients anyway, and on to a new idea. Okay, is everybody okay? Is everybody all right? Okay. All right. Now this next thing is really analogous to something we've already talked about. It's shockingly analogous to path independence. So I'm going to start by reminding you what the deal is with path independence. A weird concept. It's a property of a vector field. Special kinds of vector fields have this property. They're so special that the property itself kind of looks implausible. Let me remind you what the property is. The idea is if I have a curve and another curve C2, which you'll notice starts at the same point and furthermore ends at the same point. So these two curves have the same boundary. Same starting point, same ending point. In this scenario, I could compute the integral, line integral on C1. I could also compute the line integral on C2. Now notice I haven't said much at all about these two curves. The only requirement on these two curves is that they have the same boundary. That's it. And there are vector fields that are so special that we can say, without even knowing more information about the curves, I can say, yeah, but those line integrals always have to be equal. The value of the line integral is independent of the path that you compute the line integral on, with the asterisk that, yeah, sure, the boundary has to be fixed. But independent of the path, and therefore we call these path-independent vector fields. Okay, I hope this looks familiar. Does everybody remember path independence? Okay. Reminder, you can restate, sort of an alternative way to think about path independence is that all closed line integrals must be zero. And that's just an observation that if two line integrals are the same, then their difference must be zero. And of course their difference is a line integral that goes all the way around that boundary. And so the equivalent formulation is that that closed line integral be zero. Okay, all right. Real quick, let me make a sort of an awkward observation. Let's talk about these two curves here. Do these curves have the same orientation or do they have opposite orientation? This is a trick question, by the way. Do they have the same or do they have opposite orientation? The answer is that neither. There is no comparison between orientations on different curves. Right? If you're talking about a single curve, let's talk about C2, for example. On this curve C2, yeah, it's oriented that way. The opposite orientation on C2 would be this way. I can compare these two different orientations on the same curve because at any given point, those two options are literally negatives of each other, and it's clear how to compare them. It doesn't really make any sense to compare the orientation on C2 with the orientation on C1. They're totally different curves. They don't even have any points in common, other than the endpoints, which aren't really enough. So please don't make the mistake of thinking that you can compare orientations on different curves. Now that said, you're still going to want to kind of do it. Right? There's a temptation to look at these two curves and say, oh, well, yeah, but look, come on, they're both going kind of to the right, right? We could even kind of quantify what we mean by saying that they're kind of the same orientations because they induce the same orientation on the boundary. They both start at the same point. They both end at the same point. In that sense, it feels like they're going the same direction. Both of these trails go from the base camp to the top of the mountain. Kind of feels like they're going the same direction. Okay, but in a different sense, they're also kind of going opposite directions. C1, after all, is going what you might call counterclockwise C2 is going what you might call clockwise. So in some sense, they're kind of the same. In some sense, they're kind of opposite. They're both kind of nonsense. Neither one of them is really legitimately a true comparison between orientations. In order to resolve this seeming contradiction, the resolution is to make sure you're thinking about specifically what features you're talking about. When you say that C1 and C2 have kind of the same orientation, we're saying that they have the same boundary orientations. When we say they're kind of opposite, we mean that they have opposite signs as part of the boundary of something else. And these are two different ways to think about what is ultimately a bogus comparison between orientations on different curves. Okay, so I just needed to throw that out there. All right, pausing real quick. Does everybody remember all this path independence stuff? And if so, I'm going to now step one dimension up. We're going to talk about surface independence. Instead of curves with boundary points, we're going to talk about surfaces with boundary curves. All right, here we go. S1 is a surface. S2 is another surface, but wait a second, they have the common feature that they have the same boundary curve here. Not two curves with the same boundary points, rather two surfaces with the same boundary curve. All right? And there are some special vector fields called surface independent vector fields, and this is going to seem implausible, but these amazing vector fields have the feature that even though they're otherwise unrelated, the fluxes through S1 and S2 have to be the same. It's shocking that any vector field would have this feature, that merely knowing that the two surfaces have the same boundary, the fluxes have to be the same. Almost seems implausible. Okay, it's going to turn out that not only are there some surface-independent vector fields, it turns out there's a lot of them. And there's an easy test for it, and it's a super powerful computational tool. Okay, now I do want to phrase this a little bit differently. In order to do so, I need to talk about orientations again. Let's look at the orientation I have indicated here for S1. The orientation I have indicated here for S2. Now, are those the same or are they opposite? Well, again, trick question. You can't compare orientations. They're different surfaces. They're totally different surfaces. You can't, of course, they don't point exactly the same direction. There's just really no comparison to make because they're at different points. Right? So, okay. But nevertheless, there is a point of view that says they're both kind of up. You know, I mean, they're both up-ish. I would describe both of these orientations as oriented upward. Surely that's got to count for something. And in fact, it does. The fact that these are both oriented upward, in this case, is ultimately why they induce the same orientation on their boundary curve. And that is a requirement. When I say that these two boundaries are equal, I mean equal as oriented curves. And now this is a right-hand, finger swirl side swipe exercise. I think it's a healthy exercise. I want everybody to take a minute to do so. But this dark blue orientation on S2, side swipes and all that would give you this purple orientation on the shared boundary. And likewise, this upward dark green orientation on S1. Again, thumb, fingers, swirls, side swipes, gives you the same orientation on the shared boundary. So these two orientations are, I don't want to say they're the same, they're consistent in that they give the same orientation on the shared boundary. On the other hand, they're also kind of opposites in a way, aren't they? This one's outward, this is inward. That doesn't seem the same, that seems opposite. They are, said differently, opposite in the sense of how their coefficients are in the boundary of something else, as they are in the boundary of the solid that they defined between the two of them. Right? So again, don't make the mistake of conflating the fact that these induce the same orientation on their boundary with how they relate to the boundary of the three-dimensional solid inside of them. They're two separate questions that give kind of different points of view. Everybody okay? All right, with all of that observed, notice if these two fluxes are equal, that means that their difference is 0. The difference is the flux through the boundary, that closed surface, which is the boundary. So an alternative phrasing of surface independence is that all closed fluxes are 0. All right. Okay. So, real quick. Let's see here. Here we have path independence. Here we have surface independence. I've deliberately color-coded them, to emphasize the strength of the analogy. They're the same concept, really same concept, just one dimension up for surface independence. Okay. All right. Good news. There are lots of them. Every curl, let's see here, let me get rid of the thing. Every curl is surface independent because here, check it out. If you have a curl, and you want to compute the flux through S1, well, good news. You're computing a flux of a curl. The flux of a curl is exactly what Stokes' theorem addresses. It gives you a circulation on the boundary of the anti-curl. This is what Stokes' theorem says. Likewise, same curl. Look at the flux through S2. Well, it's a flux of a curl, therefore it's a line integral, a circulation line integral around the shared boundary of the anti-curl. And so check it out, that means that both of these integrals are computed by the exact same line integral, and that's why these two line integrals have the same value, and that's why curls are surface independent. All curls are surface independent. Okay. Okay, and furthermore, we have a local test. Now, I'm gonna go through this one really quickly, partly because we're short on time, and partly because I want to be able to give the nice punchline, and partly because we've made very analogous arguments before, and it's structurally the same idea. So I'm going to look first at these three statements. I know that every curl is surface independent. I claim that goes the other way. That's actually a hard proof. We're not going to do that in Math 219. But not only is every curl surface independent, every surface independent is a curl. And furthermore, here's an alternative way to say surface independent. Likewise, if you have some function where all the triple integrals are 0, that function must be 0. Morally equivalent argument than what we've talked about in other contexts. And we have a connection between closed fluxes and triple integrals of divergence. That connection is Gauss's divergence theorem. So now again, notice structurally it's the same argument, just kind of different players, but structurally, morally the same ideas. And that gives us our final punchline here, which is that we have this, what I like to call local test. If you want to know if your vector field is a curl of something, no problem, compute its divergence. See if you get 0. If you get 0, then yes, it's a curl. If you get not 0, then no, it's not a curl. More importantly, if you want to know if your vector field is surface independent, take the divergence. If you get 0, then yes, your vector field is surface independent. If you get not 0, then no, it's not surface independent. Okay, sadly we are going to have to leave it there, but on Friday, we will pick up there. We've got an example here that was, where surface independence is going to turn an otherwise very hard problem into in fact, very straightforward problem, and then we'll, proceed. Oh, and real quick, I just want to let y'all know, on Friday we're going to do a bunch of also really useful stuff. We're going to have a bunch of examples. I have 6 pages of examples that are designed to give you sort of practice with how to compute line integrals and surface integrals. We're going to make use of the 3-dimensional diagram to do that analysis. So I think Friday is going to be a big day. Please come and see how that works. See y'all later.